Hello everyone, nice to meet you. On behalf of all the co-authors, I will introduce our ICML paper on the nonlinearity of layer normalization in this video, and now let's start. To begin with, we know that a deep neural network usually consists of three main parts: linear layers, nonlinear layers, and normalization layers. Linear layers usually store the main parameters of the neural network. As for nonlinear layers or activation layers, they contain the main expressive power of the neural network. In previous research, normalization layers are mainly added for stabilizing training and accelerating optimization. For a long time, it is believed that normalization layer helps reach a better performance due to its advantage in optimization rather than fitting. However, in our new paper, we find that layer normalization contains nonlinearity indeed. Further, we figure out that a neural network can classify any given samples with layer normalization and linear layers only. Now we introduce layer normalization. It contains two main parts: centering and scaling. Different from batch normalization, layer normalization acts on the single input, for it does not compute the mean value among a batch of samples. Centering operation projects the sample onto this hyperplane, and we know that the centering operation is actually a linear transformation. As for scaling operation, it projects the sample onto a hypersphere with a radius of root d, contains the main nonlinearity of layer normalization. Although we can directly figure out the nonlinearity from its mathematical expression, we can hardly find its further guiding significance in neural networks. So it is important to explore how layer normalization can interact with the inputs. We use SSR and LSSR to describe how easy to separate two classes. We define SSR as the ratio of the intra-distance to the total distance. Consider all linear transformations. We define the minimal SSR as LSSR. We can easily find that if we conduct a transformation on the two classes, the new LSSR will not decrease. But we proved that layer normalization can get a smaller LSSR, which shows the nonlinearity of layer normalization. Further, we explore the nonlinearity of layer normalization from the perspective of classification. First, we can classify XOR samples correctly with layer normalization and linear transformations only. Then, we generalize it to more samples with any label assignment. Take binary classification as samples. In each step, we use layer normalization or scaling to merge 2 points from the same class. In the meanwhile, we ensure the samples from different classes are not merged. Therefore, for m samples, we can complete merging within OM steps, corresponding to an OM layers network. Finally, to amplify and exploit the nonlinearity of layer normalization, we use group-based layer normalization, which is similar to group normalization. We use Heisen metrics to measure the nonlinearity of group-based normalization, and guess it may contain more nonlinearity than layer normalization. Based on this, we conduct the experiment and identify this proposition. We first find that layer normalization has nonlinearity by fitting random labels. Then we find that group layer normalization can indeed amplify the nonlinearity of layer normalization. This is also available in practice. Finally, let's make a conclusion. We mathematically demonstrate that layer normalization is nonlinear transformation. Besides, we theoretically showed the representation capacity of an LNNet in correctly classifying samples with any label assignment. And we call for reconsidering the analysis of the representation capacity of a network with normalization layers. Thank you for your attention. If you have any questions, welcome to leave a message.